Hi friends, let us see how to design a digital Chebyshev filter. The digital Chebyshev filter can be of low pass type, high pass type, band pass or band stop type. Let us design a low pass type. So the problem for today is given to us is design a digital low pass filter using Chebyshev filter design procedure that meets the following specifications. The passband edge is given as 1 dB. The frequency, passband edge frequency is given as 2.2 pi. Stopband attenuation is 15 dB and stopband edge frequency is 0.3 pi, 2 pi, and they have said that use bilinear transformation. So let us first draw how this characteristics looks like. So let us say I keep my omega on the x-axis, then I have to have 4 parameter lines. Let's say this is my unit line, this is my AP line, this is my AS line. Okay, then I want let's say this is omega P line and this would be my omega S. Now these are all exaggerated and no scales has been used. So they are saying that I want a filter to have its passband characteristics going because I don't know the order, so I will randomly draw the ripples. Otherwise we need to be very careful by drawing the ripples in the passband. But let's say because I don't have any consideration right now, so this could be the characteristics. So this is my passband and let's say this is my stop band. Okay, so passband is given as 0.2 pi and stop band is given as 0.3 pi. Attenuation here is given as 15 dB and more, and here the attenuation is given as 1 dB and nothing else. Okay, so the 4 characteristics that are required to design a Chebyshev filter is given to us. Let us see how to design a digital Chebyshev filter. So let us go to the solution. Step 1. In step 1, we are going to find the value of epsilon. So epsilon is equal to 10 to the power 0.1 AP minus 1 the whole raised to 1 by 2. So it is 10 to the power 0.1. Okay, AP over here is given as 1 dB, so I'll put 1 minus 1 raised to 1 by 2, and epsilon according to my calculation is 0.508. So this is what the value of epsilon is. Now I'll go to step 2, which is nothing but finding the order of the filter, which is n, which is greater than equal to cos inverse of 10 to the power 0.2 AP minus 1 divided by 10 to the power 0.1 AS divided by AP minus 1 the whole raised to 1 by 2 the whole divided by cos inverse omega S by omega P. Pardon me, this is also S, 0.1 AS minus 1, not AP minus 1 in the numerator. So now we have the numerator factors are available with us because they are given in the problem, but denominator values, that is omega S and omega P, is not given to us. These are analog characteristics and the given characteristics in the problem is digital characteristics. For example, they have given us in this problem omega P, which is 0.2 pi, which is a digital frequency, and they have given omega S, which is 0.3 pi, which is also a digital frequency. I need omega P and I need omega S, right, to put in the order. So how to go from this value to this value? So in the problem they have mentioned a very important concept, that use bilinear method. This they have mentioned in the problem. So now using bilinear method, I can map the digital frequencies to analog frequencies by the relation omega p is equal to 2 by t tan of, okay, omega p by 2. Similarly, omega s equals to 2 by t tan of omega s by 2. Now we know that we have not been given any sampling frequency, so let us assume t to be equal to 1. So I assume t to be equal to 1, substituting omega p as 0.2 pi and omega s as 0.3 pi, okay, and solving further, will get the answer as omega p and omega s. Omega p comes as 0.649 and omega s comes as 1.019. Do not forget to put the units as radians per second, and here also radians per second. So now I have received my omega p and omega s using bilinear transformation. This factor, once are substituted in the formula, will give me back the order of the filter. So now the order of the filter n greater than or equal to cos inverse of 10 raised to 0.1, as is given as 15 minus 1 divided by 10 raised to 0.1, ap given as 1 dB minus 1, the whole raised to 1 by 2 divided by cos inverse of 1.019 divided by 0.649 is the order. Once you solve this in your calcs by taking the cos ratio of trigonometry, you are going to get n which is greater than equal to factor as 4.35. So I will approximate to the next highest integer to 5. So now my order is n is equal to 5. So now for the fifth order filter I need to design. Now once the filter has been, once the order has been found, you can further modify the characteristics of your filter. Here we have shown a random numbers of ripple in the when we were considering, because we were not knowing what order of the filter is going to come out from the given specifications. But now we know that the order of the filter is 5, so I will be having a total dips or the peaks and valleys to be equal to 5. So if you add the peaks and valley leaving this point will give you which should come out to be 5. Okay, so we are not going to modify it, does not requires actually to modify any modification over there, because that is only for our visualization. Okay, now let us go ahead. Once you have found the order of the filter, I can go with step 3 now to find beta. Beta is nothing but root of 1 plus epsilon square plus 1 divided by epsilon the whole raised to 1 by n. So let us calculate beta. So it will be root of 1 plus 0.508 the whole square plus 1, this is whole under root, divided by 0.508 the whole raised to 1 by 5. Therefore you are going to get beta as 1.33 is the calculation for beta. Once you have found beta, now we are going for the next step, that is step 4, to find the value of small r and capital R. Small r is omega p into beta square minus 1 divided by 2 beta. So omega p is from our previous calculations, omega p is 0.649 radians per second into beta square is 1.33 whole square minus 1 divided by 1.33 into 2. So small r comes as 0.186, very sharp ellipse it will be, because the minor axis is very small, that is 0.186. Always remember r will be less than 1 and it will be in terms of point only. So now that we have evaluated small r, let us go to find the capital R2. Capital R is omega p into beta square plus 1 divided by 2 beta. So omega p is 0.649 into beta is 1.33 square minus 1 divided by 2 into 1.33. That value of R will be 0.67. So now small r is 0.186 and capital R is also 0.67. So which is very close to 1. It should be above 1 or very close to 1. The ellipticity, the ellipse will be more elongated if r is higher, and it will be more towards circle if it is less. Okay. So now this is my capital R and small r. Now with this capital R and small r, let us go to step 5 and find theta k, which is pi by 2 plus 2k minus 2k plus 1 divided by 2n into pi. Okay. And here now k will be going from 0, 1, 2, 3, 4, because it is n minus 1 and n is the order of the filter. So I will calculate theta 0, which is equal to pi by 2 plus, now 2k, when you put 0, it will be 0 over here. So it will be pi by 10, because n is equal to 5 over here. So 2n will be 10. So that value will be 10 plus 2 is 12 pi by 20. So 12 pi by 20 can be written as 6 pi by 5. Okay. So that will be 6 pi by 10, not 5, because it is 20. 6 pi by 10. Theta 1 will be equal to pi by 2 plus, okay. Now if I put here the value as 1, it will be 2 plus 1, which is 3 pi by 10. So that factor is 8 pi by 10. Theta 2 is pi by 2 plus, now when k is equal to 2, it will be 4 plus 1, which is 5 pi by 10. Okay, so it will be 5 pi by 10, which is pi by 2. So pi by 2 plus pi by 2 will give me factor as pi. Then theta is equal to 3, k is equal to 3, so that will give theta 3, which is pi by 2 plus, now if you put 3, then 6 plus 1 is 7 pi by 10. Okay, so 7 pi by 10 will give me 10 plus 14, which is 24 by 20. 24 by 20 will give me 12 pi by 10. Okay, next I'll go for theta 4, which is the last factor, which is pi by 2 plus, okay, here if I put 4, then 4 4s are 4 2s are 8, 8 plus 1 9. Okay, this is 8, right? If I put 4 over here, 2 4s are 8 plus 1 9 pi by 10. Okay, and that factor will be 14 pi by 10. This is theta 4. So now I got theta 0 to theta 4, all the 5 factors. Why I need this? Because I need to calculate the poles. So let us calculate the poles of the filter. So step 6. Poles of the filter is given by S of k, which is equal to x of k plus j y of k, and x of k is given as x of k is given as small r cosine of theta k, and y of k is given as capital R sine of theta k. Okay, so let us let us put it in this way. I put k, which is 0, 1, 2, 3, 4. Then let us write, this is my k. What else we want? We want the factor value of theta k, that is going to get changed. Then I will have x of k, and I will have y of k, and then we will have s of k. That are the poles. So let us fill this table. So when theta is equal to 0, my theta k is 6 pi by 10, and sk value is plus 0.18 minus 0.057, okay, and yk is 0.637, okay. Once it for k is equal to 1, the factor the angle is 8 pi by 10, and the factors that I am getting is 0.15, which is with minus sign, and we are getting 0.39. Okay, for 2 the angle was pi, okay, and the S2 will be minus 0.186 and nothing, because if you put pi over here, sin pi will be going to be 0. Now third pole will be the conjugate of first pole. Here the value is 12 pi by 10, if I am not wrong. Yes, it's correct, 12 pi by 10, and it will be conjugate, so I will write 0.15, and I am going to get minus 0.39. After all, it's a cosine and a sine function. Okay, sine is odd and cosine is even. 4, it is 14 pi by 10, and you are going to get the value. If this is replicated over here, 0 will replicate over here, so it will be minus 0.057, and here minus 0.637. Now let us formulate x of k, that are the poles, which is x of k plus j y of k. X of k over here, so I'll get s of 0, which is equal to x of 0. This is x of 0, this is y of 0. X of 0 is minus 0.057 plus j 0.367. S of 1 will be equal to minus 0.15 plus j 0.39. S of 2 will be equal to minus 0.186 alone. There is no j because yk is 0 over there. S of 3 is minus 0.15 minus j 0.39, and S of 4, which is equal to minus 0.057 minus j 0.637. This is the poles of the filter. Let us go ahead and form the transfer function. So step 7 is the transfer function. So h of s is equal to k upon, okay, s minus s0 into s minus s1, so on till s minus s4 for us, because we have started from 0, right. So now we will start from s of 4. Now with this factor, what we will do is, we will say let us substitute. So h of s will be equal to k upon, okay, s of 0, s minus s0. Let us take s minus s0. When you take s minus s0, so you will get s minus S0 is minus 0.057 plus J 0.637. Okay, then we want, this is one factor. Likewise, there will be S1. So, S minus 0.15 plus J 0.39. Okay, then we have S minus minus 0.186. Here S minus 0.15 minus J 0.39. Then lastly S minus 0.057 minus J 0.637. These are the factors that I am getting. Okay. Now you can see here I can combine these two, then I can combine these two, and this will stay alone. So we have to do that now. Now let us go ahead and solve that. So combining it will be done by skipping 2-3 steps. What I'll do, I'll combine this, that means I'm getting the negative sign inside. This becomes S plus 0.057 minus this term, and when I take and I combine these two terms also over here, then this becomes plus over here, and here also it becomes plus. So what I'll get is A, this will be minus B, and this will be A, and this will be plus B. So A minus B into A plus B will be written as A square minus B square, and we have J square over there, so it will be plus. So I'm going to get S plus 0.057 the whole square, okay, plus 0.637 square. This is one term. The second term is S plus 0.15 the whole square plus 0.39 square. This is the second term. Lastly, the third term is S plus 0.186. This is the third and the last term. Now let us calculate, open up the bracket, multiply and get the transfer function. After opening up the bracket, we will get the transfer function h of s as equal to k upon, okay, so we have the first bracket open, so let me keep it like this, s square plus 2 into 0.057, okay, plus 0.057 square plus 0.637 square. Then we have s square plus 2 times of 0.15 plus 0.15 square plus 0.39 square. And lastly, we have the final term, that is s plus 0.186. Okay, so we have opened up the bracket and we have written it in this term. Now, after doing the squares of these two terms and adding them together, and then here I missed one s, so here it's an s, here there is also an s, okay, because you will have s square plus 2 times of this into s and then so on and so forth, okay. So now I will multiply this, I will add this two squares, I will multiply with 2 and all the things will be done, and the final transfer function will be k upon, okay, I will write it directly, 0.186 into s square plus 0.3 s plus 0.1746. Next term is s square plus 0.114 s plus 0.409. Okay, so these are the basic 3 terms that we are going to now work on with. Now readers are also encouraged to solve this further, but then it will make the system more cumbersome. Let us keep k as it is without putting any value for k, that is a constant factor. We'll keep k as it is. So if you multiply it further, you are going to get s raised to 5 term, and then there will be some multiplying factor to it, and then you have to divide the whole by. There will be huge number of calculations thereafter. To avoid that number of calculations and mistake, what I will do is I will keep my h of s in this form only. So this is my analog transfer function. But this is not the end of the problem. The problem states us that we need to design a digital Chebyshev filter, and we are not supposed to give h of s, but we are supposed to give h of z in this case. So we need to add one more step to now. So the last step was step 7. So let us go to step 8 now, and let us obtain h of z. Now h of z is equal to h of s in bilinear transformation. If I replace s by 2 by t, 1 minus z inverse upon 1 plus z inverse. So I need to replace my s's by 2 by t, 1 minus z inverse upon 1 plus z inverse, and we will assume t to be equal to 1 second because the sampling frequency is not given. So let us assume t is equal to 1 second, and let us substitute and give the final result. So h of z will be equal to, okay, my h of s is a very big number, so I'll write k upon, now the first term is s plus 0.186, so I'll write s plus k, s I will replace by 2, 1 minus z inverse upon 1 plus z inverse, that is for s, plus 0.186, that is second term. Next, s square. So now it's a big deal because you are going to have 2, 1 minus z inverse upon 1 plus z inverse, the whole square, plus 0.3 into s, so it is 2 into 1 minus z inverse upon 1 plus z inverse, okay, do not miss a single term, plus 0.1746. So this is my first term, this is my second term. In second term I had s square plus 0.3s plus this. So s square I have put this, replace this in the place of s square, and this I have got. Let us write the final third term. Again I have s square over there, so I'll write 2, 1 minus z inverse upon 1 plus z inverse, the whole square, plus, okay, I have 0.114 times of s, so that is 2 times of, okay, 1 minus z inverse upon 1 plus z inverse, plus 0.409. So that is the end of the third term, and this is the required transfer function. Does not look very pretty, but then once you have a full span of page, use a full span of page and write the transfer function. Do not miss a single term. So replace all s's. Wherever you get s in h of s, you have to replace it by 2 by t, but t we have assumed it to be 1 second because sampling frequency was not mentioned in the problem. So that is what the transfer function of a Chebyshev filter with the fifth order is. Now how you will say, how will you get fifth order? See, here you are going to get one z inverse, here you are going to get another z inverse, but here it will be z raised to minus 2 because it is going to get squared, and here also you are going to get squared. So this square and this one will give you z raised to minus 5. So order will be fifth order digital filter. So this is how there are 8 total steps to design a digital Chebyshev filter. Thank you.